Everyone, I'm Satya K, research scholar working under the guidance of Dr. K.P. Guruswamy in the Department of Electrical Engineering, UVCE Bengaluru, India. My paper ID is 39287. I am here to brief in about analysis of LLC resonant converter performance with PID-D2 controller for electric vehicle application. These are the contents I cover, which includes introduction, problem statement, objectives, methodology, advantages and operation of LLC resonant converter, modeling and design, PID controller, PID-D2 controller, results and discussion, conclusion and references. Well, usage of fossil fuels has led to climate change due to emission of carbon dioxide. Then comes public health hazards. Hence, there is focus on clean energy technology, mainly into transportation. Therefore, electric vehicles are considered as main part of it. Quick charging and high power chargers are required to increase the usage of electric vehicles. In order to address this demand, LLC resonant converter play a vital role with high power density, low noise, and high efficiency. In conventional switching patterns, as shown in figure A, during turn on and turn off of power semiconductor devices, this switching loss manifests. And this can be overcome with the help of soft switching techniques, which is shown in figure B. So in this switching, transition occurs under favorable conditions when device voltage or the current is zero. And that leads to reduced switching losses and switch stress, and also possibly it lowers the EMI. Because of lower switching losses, there is easier thermal management. Soft switching is really a must for very high switching frequencies, also at medium frequency at high power levels. Soft switching would achieve us zero voltage switching or zero current switching. So zero voltage switching occurred when voltage across the device is zero. And zero current switching occurs when current through the device is zero. So this has advantages, as mentioned before. It lowers the losses, lowers the EMI, allows the high frequency operations. Hence, hence in this paper, based on the literature survey, the problem statement has been identified. And here what we have found out is that shortcomings of charging techniques in electric vehicles are there. And because of that, we have circuit topologies implemented, which is of high efficiency and less switching losses, and power semiconductor devices are minimally stressed. And another problem would be the existing concepts has complex control structures and complicated control algorithms. Hence, in order to overcome this problem, we have come up with the objectives, which is to analyze the working of resonant converter LLC with the help of equivalent circuit diagram, and to develop accurate mathematical model to determine the specifications of LLC resonant converter with the design of PID and PID-D2 control. And this is validated with the help of MATLAB Simulink. So based on the objective, the methodology has been mentioned, wherein derived Ohm's law technique is used in order to obtain the output voltage under steady state and plot the performance with line and load variation. Extended describing function modeling technique is used in order to obtain the output voltage to change in frequency. PID and PID-D2 control methods are being used in order to improve the transient response. And along with that, it has been verified using MATLAB Simulink platform. So in order to regulate this output voltage of LLC resonant converter, there are several methods like proportional integral, PI, PID, PD, etc. But these do not guarantee intended performance under different operating conditions. Hence, in this paper, specifically, it has been addressed voltage control issue using PID-D2 control design techniques, which has not been discussed in or investigated in any other literature so far. And it has been compared with PID and PID-D2 controller, and its effectiveness is verified using rise time, overshoot, and settling time for sudden changes in input voltage and load. These are the advantages of LLC resonant converter, that there is electrical isolation between input and output, and zero voltage switching, which occurs during turn on, and zero current switching, which occurs during turn off. And there is high efficiency because of minimal switching losses, and there is low voltage stress, and wide output voltage variation can be attained with the help of this, and high power density is provided in LLC resonant converter. Then we have operation of LLC resonant converter. The figure 1 shows the circuit topology of LLC resonant converter, wherein we have two MOSFET switches, and then we have LLC filter circuit, and then we have a transformer, and then a rectifier circuit, and then we have load. Okay, so complementary power switches Q1 and Q2 is managed to control the frequency of switching network with fixed duty cycle of 50%. This generates the square wave, and this is given the square wave which is generated is received by this LLC tank, which consists of resonant capacitor, resonant inductor, and then magnetizing inductance. And then we have our this transformer with a turns ratio of N/1, which supplies and circulates the energy to the load through the rectifier. And the circuit parameters are determined with these relevant equations for designing LLC resonant converter. So figure 2 shows the variation of input voltage with respect to gain for different values of N from 15 to 19. So each line in this figure represents different values of N. Gain decreases as the input voltage increases. So the gain is highest at N is equal to 19, and it is lowest at N is equal to 15. And the variation of input voltage from 370 to 410, and variation of input voltage and variation of a gain from 0.86 to 1.21 for different values of N we can see here. And figure 3 shows the variation of Ln, that is inductor ratio with respect to Lm, magnetizing inductor. Choosing the right inductor is also a very important aspect. And figure 4 shows the variation of quality factor with respect to the equivalent resistance Re. In this paper, our aim is to obtain the optimum values of quality factor, gain, turns ratio, and inductor turns ratio for enhancement of LLC's performance. So based on the optimally chosen values, the controller comparison is being made for respective design. And design specifications are tabulated in table 1. And these are the spec we have considered for the controller comparison. And the modeling technique is used, that is the extended describing function. And the system transfer function is derived as shown in this gain G. And its equation is obtained in this way. And the modeling technique we have used is pulse frequency modulation technique. And then comes the necessity of controller. The main objective or the main objective of the controller is to have the steady state error 0 and to obtain the fastness of the control and to attain the stability of the control. So in order to achieve this, we need controller. So PID and PID-D2 controller is what we have used. And the controller, the sensor network senses the output voltage, and so this has been compared with the reference voltage, and this in turn would give us the error voltage. So error voltage is given to the controller. So based on this error voltage, the frequency has been adjusted. The frequency, that is pulse frequency modulation. So based on that, frequency has been adjusted in the controller, and it's given to the switches through the gate driver. It is given to the switches, and it has been again sensed with the help of sensor network. So in this form, the controller operation takes place. The figure 5 shows the schematic of the controller representation with the LLC resonant converter. And PID controller, this is one of the control loop feedback mechanism, wherein error signal E of t is related to the control signal U of t, in which Kp, Ki, Kd represents proportional, integral, and derivative gains. And using Zeeler-Nichols tuning method, the values of Kp, Ki, Kd can be calculated, and this is to optimize the controller performance. And this is the transfer function of PID controller. Then comes PID-D2 controller. The schematic of PID-D2 controller looks like this. And the other variant of PID controller, which is also known as double derivative PID controller. Unlike conventional PID controllers, this version includes a second order derivative term, which is Ka. And the transfer function of the PID-D2 controller is given as G of S. And the PID-D2 controller improves system stability, and it shortens settling time response. Gain coefficients of Kp, Ki, Kd, and Ka are determined using Zeeler-Nichols tuning method. Here comes the simulation results and discussion. Figure 8 shows the Simulink model of PID and PID control model with line variation. And line variation is executed from 368 to 420 volts. And the respective response of the controller for variation in the line has been shown in this waveform. And table 2 tabulates the variation of the performance with respect to rise time, settling time, and overshoot can be seen for PID controller and PID-D2 controller. And it is shown that PID, it can be seen from the table and also from the waveform that PID-D2 controller performs better compared to PID controller. Here is the model for load variation, the Simulink model for the load variation of PID-D2 and PID controller. And the load has been varied, load current has been varied from 2 amperes to 25 amperes. For the variation, the output voltage performance can be seen in terms of PID and PID-D2 controller, and it has been tabulated in table 3. And it is seen that PID-D2 controller performs very better compared to the PID controller in terms of rise time, settling time, and overshoot. With that, we can conclude that basic principle design modeling of LLC resonant converter for wide variation of supply, voltage, and load variation has been explained in this. PID and PID-D2 control mechanism has been implemented, and it is seen that PID-D2 controller is the potential choice for a line and load variation in comparison with PID controller. And it has been verified using MATLAB Simulink platform. These are the references which I have referred. And with that, A big thanks to editors, reviewers, and everyone who are part of IJEECS team for your valuable comments and suggestion. It helped me shape this paper in a very good form. Lots of gratitude to my mentor, Dr. KP Guruswamy, all faculty members, head of the department, electrical engineering, and everyone who have been very supportive in this process. Thank you, one and all.